Now we start with stability analysis in state space. In this, first part is concept of eigenvalues and eigenvectors. In this eigenvalues and eigenvector, we will study introduction to eigenvalues and eigenvectors, definition of eigenvectors, definition of eigenvalues, properties of eigenvalues and numerical example. Now, introduction to eigenvalues and eigenvectors. The most important thing is that these eigenvalues and eigenvectors are useful in control system. In control system, we have discussed earlier, the control engineer has to perform modeling, then he has to check stability, then he has to design a controller. For all these issues, eigenvalues plays a very much important role. If there is no eigenvalue, no control system, or we can, in other words, we can say eigenvalues and eigenvectors is the heart of the control engineering. And now what is control engineering? Control engineering is applicable to all type of system. It may be electrical, mechanical, civil, computer. Therefore, as eigenvalues plays important role in control system, so these eigenvalues are also plays important role in all type of systems. For example, if you take a rigid body and if you move up, so it will rotate, so it has some axis of rotations. So this axis of rotations is called eigenvector and its moment of inertia is called eigenvalue. If we can consider another example, that is if you consider the vibration of a mechanical systems. In that case, the natural frequency of vibrations, that is called eigenvalue, and it's particularly we can say the mode of these vibrations, that is called eigenvector. So these eigenvalues and eigenvectors are useful everywhere where is the system. Now how to define these eigenvalues and eigenvectors? Now we will see definition of eigenvectors. Suppose Ax equal to y, where A is n cross n matrix, x is n cross 1 matrix, y is n cross 1 vector. From above equation we can say that n cross n matrix operator A operate on n cross 1 vector x, we get new transform n cross 1 vector y. That is, we have a matrix which is of order n cross n. When it is operated on x which is of order n cross 1, we can get y which is of order n cross 1. That is, A operated on x, we can get a y. For example, if I will take the example, let us say A equal to 1, 2, 3, 4. What is the order of A matrix? Order of A matrix is 2 cross 2. And now this has to operate it on x. Let us say x is a vector, that is n cross 1, that is say here 1, 2. Now this is x. So order is 2 cross 1, 2 rows 1 column. Now what output will get? Output y is nothing but the rows. What is row? Rows, these 2 rows 1 and 2 operated on column, this column. So what will get? Here 1, 2 plus 2, 4, we will get 5, and here this row operated on this will get 3 plus 8, 11. That is, y will get as 5, 11. Now another definition, eigenvectors of a system matrix A are all vectors xi not equal to 0, which under the transformation of matrix A becomes multiples of themselves. That means here eigenvectors are non-zero, they are never be 0. That means here it is mentioned that A xi, that is A operated on this vector which is non-zero, become multiples of this themselves. That means we can write down as lambda into xi. A xi equal to lambda xi. That means here this what is happening here, a matrix operated on X and we get the new vector. So you will find that in that case you have to see what is the directions. So it is along the same directions. So here it is shown eigenvector, that is third definition. Eigenvector can also define as vector X such that matrix operator that is A matrix transforms it to a vector lambda X. We have told earlier that Ax equals to lambda X. So here it is mentioned same thing, to vector lambda X. This vector have the same direction in state space as the vector X. If you take any variables, it has a magnitude and directions. Okay, so after transformation, if the direction remains same, then that is called eigenvector. If the direction is not same, then we can't call as a eigenvector. For eigenvector, this vector should be always non-zero, it should not be 0. That means here I am showing, see here x1, x2. Now here this is Ax, and now let us say lambda X. So this is not valid. That is, this Ax and lambda X must be in the same directions. So here I am showing it again. So here x1, x2. Now here I am showing say Ax, and I can say it is lambda X. Then this is called eigenvector. This is correct. Now what are the definitions of eigenvalues? Actually eigenvalues is nothing but the combination of German and English, so because here there are two words, eigen and values. Therefore here eigenvalues is the combination of German and English word. In this, German word is eigen and English word is value. English word is value. The meaning eigen is characteristics, and the meaning of value, the characteristics of the system. Value means characteristics of the system, and whereas eigen is nothing but the characteristics. Now how to define eigenvalues? Eigenvalues of a matrix A are the values of lambda that satisfy the equation Axi into lambda xi, and as I told, xi should not be equal to 0. So this is the definition of eigenvalues, and here lambda I is nothing but the eigenvalue. That means A operated on X, that is sketching of the vector, and because lambda is that means sketching, vector is being sketching, length has been increased, that is basically an eigenvalue. So the factor which helps in sketching, that is called eigenvalue, and X is the eigenvector. Now why the eigenvalues of the system matrix is defined as A minus lambda I equals to 0, means whenever we calculate the eigenvalues, why it says that A equals to lambda I. So for that purpose what we do, we write this Axi equal to lambda I into xi. Now this equation, assuming an identity matrix Axi into lambda I into xi, then we write this equation A minus lambda I into xi lambda into I equals to 0. That is A minus lambda I into xi equals to 0. We are replacing all the elements on the one side, and it is said that A minus lambda equals to 0. That is the way to calculate the eigenvalues, but we should know why it is so. So for that purpose we have taken the same equation and then I have solved it. I have come here. Now how to do it, how to move further? So now what I have done, this xi equal to A minus lambda I to A inverse to 0. Now here we have got 0 and this is the inverse, so xi becomes zeros, but the condition of eigenvalue is that xi should be never 0. Even earlier definition we have seen eigenvector should never be 0, it should be always some value. But if you see the literature, it is says in order to calculate the eigenvalues we have to make a minus lambda I equal to 0, but here we have got this equation. Therefore, what we can do here, if you write this equation a minus lambda I inverse, so it can be written as adjoint of a minus lambda I divided by determinant of a minus lambda I by into 0, that is xi. So now here this, in order to have xi to be non-zero, what is the possibility? Because this cannot be 0. If this is 0, this total piece is 0. So that means if this factor is 0, then 0 by 0 cannot be defined, undetermined. And therefore, in order to check the stability of the system or the particularly we can say eigenvalues, we have to check a minus lambda I equals to 0. Now we have to see some properties of eigenvalues. First, for any general matrix, if the coefficients of the matrix A are real, then its eigenvalues are always real or complex conjugate pair. That means here if I am saying A is matrix, it has some elements 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the elements. So eigenvalues of A, if you calculate it like this, lambda I minus A, so that eigenvalue can lie on the real axis or it may be complex conjugate. So any possibility will be available when a given matrix is real and it is general form. Now we are coming to real symmetric matrix. If matrix A is real symmetric, what is real symmetric? The rows and column elements are same. That is, if you say take any matrix, if the row elements and the column elements are same, in that case that matrix is called real symmetric matrix, and when the matrix is real symmetric, their all eigenvalues are lying on the real axis. There will be no complex conjugate eigenvalues. Here it is written, if matrix A is real symmetric, row and column elements are same, then the eigenvalues are always real, no complex conjugate eigenvalues. For example, if I write this for this part, here I write 1, 4, 6, this is row. Now I am taking element here 4, 6, then I can write 5, that is 6, 8, you can take 8 here and 7. See here 1, 4, 6, 1, 4, 6, 4, 5, 8, 4, 5, 8, 6, 8, 7, 6, 8, 7. So this is real symmetric, and in that case the eigenvalues of this are lying on the real axis only. That is this part. Eigenvalues of a matrix A and its transpose. The eigenvalues of A and its transpose matrix are always the same. That means if you take the A, let us say A matrix has eigenvalues lambda 1, lambda 2, lambda 3, and if you make transpose of this, so we will always get the eigenvalues lambda 1, lambda 2, lambda 3. Eigenvalues of matrix A and its inverse, that is A inverse. Suppose if your matrix A has eigenvalues lambda I equals to 1, 2, 3 up to n, just like this is, and if you make it A inverse, so A inverse has also eigenvalues. So in that case the eigenvalues are nothing but 1 upon lambda I, where I equal to 1, 2, 3 up to n, that is this part. Eigenvalues and determinant. The product of the eigenvalues of a matrix equals the determinant of the matrix. See here, if whatever the eigenvalues are there, if you multiply it, that is nothing but the determinant of a matrix. Then trace eigenvalues and the diagonal elements. In a previous part we have seen that using the trace of the matrix we can determine the transfer function model of the system. So, here the same trace, the trace is nothing but equal to sum of eigenvalues, that is what, let us say lambda 1, lambda 2, lambda 3 up to say lambda n. Similarly, sum of diagonal elements is also equal to the trace of the matrix, that is if you take trace, the diagonal elements, let us say a11, a22, a33, ann. So, this concept, the trace equal to sum of diagonal elements, we have already used in determining the transfer function from a given state space model. Then singular matrix and eigenvalues. Matrix is singular if and only if it has 0 eigenvalues. Matrix is singular, singular means the determinant is 0. Let us say this is determinant delta, and let us say these are eigenvalues lambda 1, lambda 2 up to lambda n. What is said, it has 0 eigenvalue. So, 0 eigenvalues, why? Because when singular is there, open delta equals to 0, the delta means determinant equals to 0, and this is only possible when one of the eigenvalue is equals to 0, lambda 2 equals 0 or lambda n equals to 0. Therefore, it is shown that matrix is singular if and only if it has a 0 eigenvalue. Now, 0 eigenvector and 0 eigenvalue. Eigenvalue can be 0, but eigenvector cannot be a 0 vector. That means we have written Ax equal to lambda x. So, what is said, eigenvalue can be 0, but eigenvector never be 0. That means theoretically it is possible that A0 into lambda 0, but what about the actual things, because actually eigenvalue can be 0, but eigenvector never be. For that purpose, let us say if I taken a matrix as 1, 2, and here we can take 2, 4. So, we can write down this as here -2, 1 equal to. So, what will get? You will get it as this is x, this is a. So, here Ax has been multiplied, so it gets -2 plus 2, and here we will get -4 plus 4. Now, here it is 0, 0. So, now x we have taken here. Now, what we can write? We can write lambda x. So, we get lambda x equal to 0. So, now we can write lambda, and what is x? X is -2, 1, that is equals to 0, but this is not 0, this x is non-zero, that means possibility that lambda equals to 0. That means eigenvalue can be 0, but this is not true for eigenvector. Same eigenvector cannot be associated with different eigenvalues. Suppose if you have taken Ax equal to say lambda 1x, and then we can also take Ax equals to lambda 2x. Assume that x is the eigenvector for lambda 1, x is the eigenvector for lambda 2. Now, if you equate it, what will get? Lambda 1x equal to lambda 2x. Then if you solve it, we will get lambda 1 minus lambda 2 into x equal to 0. And what about this x? X is the eigenvector, so it can never be 0. Eigenvector cannot be 0. So, the possibility is that then lambda 1 minus lambda 2 equal to 0. That means lambda 1 equal to lambda 2, but we have taken different eigenvalues. That means this is not possible. Therefore, we have written same eigenvector cannot be associated with different eigenvalues. Now, we will solve example and from this example we will see how to determine the eigenvalue and eigenvector. Now we have taken example, a matrix A equal to 0 1 minus 2 minus 3. This is a matrix and our problem is we have to calculate the eigenvalues of this matrix. So how do you determine it? So first of all we write this A matrix as lambda I minus A. Lambda I minus A. I is the identity matrix. So here after replacing identity matrix and lambda we get lambda minus 1 2 lambda plus 3. Now what is the next step? Now we have to take the determinant of this matrix. So determinant of lambda minus A, that is equal to, you solve it, lambda into lambda plus 3, that will be this multiplication, minus this is minus 2 equal to 0. So we will get lambda square plus 3 lambda plus 2 equal to 0. So if you solve it we get lambda plus 1 lambda plus 2 equal to 0. So lambda equals to minus 1 lambda equals to minus 2. That means we have two eigenvalues, one is say lambda 1 equals to minus 1 and lambda 2 equals to minus 2. These are two eigenvalues. Now our main purpose is to determine the eigenvectors. Now how do you determine the eigenvector? Now first of all we determine the eigenvector for lambda 1 equal to minus 1. So which equation available to us? We have same equation, that is lambda 1I minus A into x equal to 0. Lambda 1, because earlier we have taken this lambda, but now we have got two eigenvalues lambda 1 and lambda 2, therefore I have changed lambda to lambda 1. So lambda 1I minus A multiplied by x equals to 0. So now we write the equation as lambda 1 0 0 lambda 1 minus A, what is A matrix? A matrix is 0 1 minus 2 minus 3, complete. Now how many states? x1 x2 equal to 0 0. Now we have to solve this equation. So after solving what we will get? We will get equation as lambda 1 minus 1 2 lambda 1 plus 3 x1 x2 equal to 0 0. Now in this equation we replace lambda 1 equals to minus 1. So this lambda 1 equal to minus 1 we have to replace. So what we will get? We will get it as minus 1 2 2 and x1 x2 equal to 0 0. Now if you solve it, what will get? Minus x1 minus x2 equal to 0. Second, 2x1 plus 2x2 equal to 0. Both are the same equations. That means if you take x1 equal to 1 and what is x2? In that case x2 equals to minus 1, because here x1 x plus x2 equal to 0. Therefore for lambda 1 equals to minus 1 our eigenvectors are x1 x2, that is equal to 1 minus 1, that is x1 is 1 x2 equals to minus 1. So eigenvectors are 1 minus 1. Now next what we want? We want eigenvectors when lambda 1 equal to minus 2. Now for lambda 2 equals to minus 2, so we write the equation as lambda 2 minus 1 2 lambda 2 plus 3 x1 x2 0 0 and now replace lambda 2 equals to minus 2 in this equation. So what we will get? We will get minus 2 minus 1 2 1 x1 x2 equal to 0 0. Now we solve this equation. So after solving we will get as 2x1 minus x2 equal to 0, and second equation 2x1 plus x2 equal to 0. That means this equation for this and this is for this, and we will find that again they are the similar equations. That means 2x1 plus x2 equal to 0. Suppose if you take x1 equal to 1, so what is x2? x2 equal to minus 2. Therefore when lambda 2 equal to minus 2, your eigenvector is 1 minus 2. Therefore for lambda 1 equal to minus 1, we have got eigenvector as 1 minus 1, and when eigenvalue lambda 2 equal to minus 2, we have got eigenvector as 1 minus 2. Now this is a second order system and we have solved easily, but if we increase the order of the system, this process is quite cumbersome. Therefore we want a method which can give easily the eigenvectors. So in literature there is one method which is called cofactor method, which we have already seen in the Leverrier algorithm, that methodology can be useful to get the we can say the eigenvector of a system, or eigenvectors can easily determine by the concept of the cofactors. So how do you determine it? So for that purpose I am taking the same example. See here, for lambda 1 equals to minus 1, we have got this equation, and after that we solve. So what we are doing, we are not moving these steps. So what we are doing here, when lambda 1 equals to minus 1, we have got a matrix as minus 1 2 2. You just can check it. So minus 1 2 2, just you can see here minus 1 2 2. Now we want the eigenvector for this one. So what we can do, the eigenvector now cofactor means we have to take the minors. So for minor of this minus 1 is 2, whereas the minor of this is 2, but because here it is in the second row first column, so it is odd, so we will get this as minus 2. That means we divide by 2, both this 2 and 2 will get 1 minus 1. So you find that we will get the same 1 minus 1. See, without doing any calculations we have directly get the eigenvector. Similarly when lambda 1 say lambda 2 equals to minus 2, so what matrix we have got? We have got matrix this, that is we have got minus 2 minus 1 2 1. Now we want eigenvector for this. So eigenvector so what we do, we have to take the principal minors. So for this minus 2 it is 1, and for this 2, but because here 2 plus 1 3, this is odd number, that is 2 rows first column, therefore it becomes minus 2. 1 minus 2 1 minus 2 1 minus 1, here 1 minus 1. That means we have easily determined the eigenvectors of a given system matrix. Now here we observe that here eigenvalues are distinct, but it may possible that sometimes the eigenvalues are repeated. In that case, how to calculate the eigenvector? Now we start solving the example on generalized eigenvector. So I have written a matrix A as A equal to 0 1 minus 1 minus 2. So if you solve it, so what will get? Lambda I minus A, if you solve it, we will get it as lambda square plus 2 lambda plus 1 equal to 0. So, we will get it as lambda 1 equals to minus 1 and lambda 2 equals to minus 1. So, these are two eigenvalues we have got for this matrix 0 1 minus 1 2 minus 1 minus 2. Now, but eigenvalues are repeated. Now, how to proceed further to get the eigenvector for such type of problems? So, for that purpose what I am doing here, we will take, so here lambda 2 we have taken, we can see lambda 1 equals lambda 2. Now, how will we proceed further? So, what I will do here, I will write equation as lambda 1 I a equal to lambda 1 minus 1 1 lambda 1 plus 2. Next, we write this as for lambda 1 equals to say minus 1. So, when what we will do, when lambda 1 equals to minus 1, we can write down this as minus 1 minus 1 1 1. Now, in order to get the eigenvector, what we take? We will take this part as a cofactor part. So, we can write down as 1 and for this we can write down minus 1. That means we have got eigenvector for lambda 1 equals to minus 1. Now, problem is that we want to determine the eigenvectors for another one. So, what we can do here, we can take what we do, we can for lambda 1 equals to minus 1, this the cofactor for this is lambda 1 plus 2 and cofactor for this minus 1 is minus 1. That means for lambda 1 equals to minus 1, by conventional method we have got it, but to get the eigenvector for another lambda 1 which is equals to minus 1, what we have done, from the physical variable itself I have taken lambda 1 plus 2 and for this minus 1 I have to minus 1. Now, what we do, I will differentiate this equation, that is what we will do, differentiation with respect to lambda 1, that is lambda 1 plus 2 and differentiation of lambda 1 with respect to this minus 1. So, if you differentiate it, so what we will get, here we will get 1 and this is get 0, 1 0. This is the eigenvector for lambda 1 equals to minus 1, that is second eigenvalue, and original eigenvalues lambda 1 equals to minus 1, we have got eigenvector as 1 minus 1. That means whenever we get whenever we need to determine the eigenvectors, what we do, we have to write the equation in terms of generalized form, then express this, write the minors, and that minus we have to differentiate and then replace the values, you can get the eigenvectors for a repeated eigenvalues. Now, these are some references: I.G. Nakrat, M. Gopal and N. S. Nice. Thank you.